Hello, everyone.
Hi, Doctor.
I hope you have a nice break last week. Let us continue our discussion on neural machine translation. So last time we were at where? Uh,
Happy Eid, يا دكتور.
Happy to you too. Thank you. Okay. Yeah, we finished that. Okay. I think we were here. Okay. So before I eat, we were talking about the neural machine translation that we need to convert from an input sequence to an output sequence. It was a sequence to sequence. And the application was machine translation, neural machine translation. And this is the architecture that we were talking about, that we have an encoder, recurrent neural network like this, and we have the decoder. So in the encoder, we present uh, our words, our tokens, one word after the other. And we started decoding by issuing a start symbol for the decoder. And the decoder is using the last hidden state of the encoder. As you can see here, it will use the last hidden state of the encoder as its H0D, for example, the initial state of the decoder. And we'll start to regenerate the output, and every output will be used as the next input, the teacher enforcing mechanism that we talked about before, right? So the question here is, are there any issues that are associated with this traditional sequence to sequence? Yes, and as actually stated here, that the entire meaning of the sentence, the input sentence or the input sequence, is packed into one embedding. The very last embedding of the encoder is supposed to capture the meaning of the entire input sequence. And uh, after that, the encoder will never interact with the decoder. So the decoder is on its own, or as it says here, hands-free. It does not communicate back with the encoder whatsoever. The only time the decoder interacts with the encoder is at uh, the first time the decoder will start to produce an output. It will take the hidden state or the last hidden state of the encoder to generate its output. The question is, or the suggestion was, what if the decoder pays attention to the encoder's hidden state? I mean, what will prevent the decoder from looking at the encoder hidden states at different time? The encoder is there as a network, and the output of every hidden state could have been provided somehow. This is what they call attention. So the decoder was trying to attend to the encoder's hidden state, and was actually like a sort of revolution of how the sequence to sequence is working. And the idea behind this attention mechanism is that when we translate, we humans, when we translate any statement, we don't use original sentence, the entire original sentence. And then we start to think about the meaning of the last word. We don't look at only the last word. But as it says here, we continuously think back at the original sentence. We attend to the different words of the original sentence. And this is what they try to imitate in this attention mechanism. It goes back, this attention concept goes back to uh, uh, cognitive neuroscience. It's very, very old, actually, from the 1800s. And it was used in kernel regression in 1964 by locally weighting its prediction. Remember when we talked about regression with Dr. Marwa, when you say that our y hat is, let us say, a1x1 plus a2x2 plus anxn, these weights will have different values. The higher the value, the more attention you are paying to this feature. The lower the value of this A is, the lower attention that you are paying to this feature. So you can think of the weights of any regression model as if it is actually some sort of attention. So let us see how it is going to work. How can we apply the attention to the sequence to sequence network? So how can we determine the value of every word in the encoder? So let us say, for example, that we have this a sequence, the brown dog ran, four words, four tokens. We can say that the first word there will have, let us say, a weight of zero point 0.4. The second one has zero point 0.3, or zero point 0.1, and zero point 0.2. This will be the weight of the four words, let us say, to produce the first output from the decoder. As you can see, the summation of all these values are 1 in order to uh, uh, have some sort of probability of how much the output, the first output of the decoder will depend on the in any of these words. So what will happen that when we start our decoding, when we start the decoder by providing the start symbol, and we have the hidden state of the decoder, and we will assume that all of the encoder's hidden layers are available. So let us assume that we're going now to, the decoder will attend to every hidden state of the encoder. So we have 4 hidden state of the encoder. So let us say that we're going to use, let us say, another neural network, small neural network, that will be provided by the hidden state of the encoder and the first hidden state of the encoder, which somehow encodes the word that. And that will produce an output, let us say, of just one output, 1.5. So we're going to use like a function. This is a function. Let us say that this is another function. This neural network is a function that operates on the first hidden state, the hidden state of the encoder, any one of them, and the first hidden state of the decoder. The second word, or the second hidden state of the encoder, will produce a value with the same hidden state of the decoder, will produce a value of 0.9. And the third one will produce a value of 0.2. The last one will produce a value of negative 0.5. So in this case, what we need to do, we have like what we call row scores. This represents the uh, the function that applies over the hidden state of the decoder, the first hidden state of the decoder, and all the hidden states of the encoder. As you can see, the row scores are positive, negative. It could be any value between negative infinity and plus infinity. So we need to normalize this, and as usual, we are going to softmax these values like this. Take the exponentiation of each value and divide by the summation of this exponentiation. This will turn these values into what we call attention values. So A11 will be A1, the superscript refers to the decoder first hidden state, and the subscript refers to uh, the particular hidden state. So when we say Aij, so this is the decoder and this is the encoder. So by soft maxing these, we get 0.51, 0.28, 0.14, 0.07. It makes a lot of sense because the first word that will be produced by the decoder very much depends on the first word in the input sequence. So we're going to create what's called the context uh, vector, C1D. So one for the first word of the decoder and D for the decoder. So in this case, we're going to have, uh, we're going to use A1, A11, A21, A31, A41 to produce the C1G. And then we're going to concatenate the already given hidden state of the decoder, which is produced by the input symbol here, S, and the context state that is created from the encoder. This will produce let us say, a larger hidden state of the decoder. And this larger hidden state will produce the output, the first output. So what is new here is that instead of using the very last hidden state as in the conventional sequence to sequence, we're going to use, as you can see here, a linear combination of the four hidden states of the encoder, and we add them to the current hidden state of the decoder to provide a larger hidden state of the decoder. So these values, the A's, will actually provide some sort of attention for each word of the input sequence. When we use for the next statement, or sorry, the next word in the decoder, we use the output as a new input for the decoder. We need to produce the second word. So in this case, we're going to create the hidden state of the decoder as usual, but we're going to add to it another context vector coming from the encoder by producing four A's, but they will correspond to a second output of the decoder, and each one will correspond to one of the hidden states, the four hidden states, by using the same function that we used before. And we keep doing that till we finish the entire sequence. So we have four words here as an input sequence. The output is five words. But as you can see, every time for the decoder, in the original in the original sequence to sequence, we were using this the last hidden state H4E to go with the first hidden state of the decoder. Now we are not doing that. We are taking combination of four hidden states of the encoder to be combined with the current hidden state of the decoder to produce the output. So if we look at how we do that, so we have this first, we have the attention input. So we have all the encoder hidden states, S1 up to SM. In our case, it was H1 to H4. Here it is S1 to SM, assuming that we have M hidden states. So the input sequence has M words. And we start with the decoder. We have HT at time T. Then what we do for every M of the hidden state of the encoder hidden state, we calculate the score between HT at time T and every hidden state. So this score will measure how relevant the kth token to the time step or the output time step from the decoder. Then after calculating the scores, we do a softmax and we get A of K at time T, A of token K at time T of the decoder, which is exponentiation of every score, HT and SK, over the summation of all scores. K goes from 1 to N. Then we create the context for the decoder step T by using those A's with S by a linear combination like A1 at time T S1, A2 at time T S2 plus AM at time T SM, which is this summation. And this is the context vector that will be added to the HT. Not added, actually, will be augmented. I mean, we're going to have like a larger vector H CT and HT. And this will be the new hidden state of the decoder. Of course, this score function doesn't have to be a neural network, could be anything. There are many ways to do that. Like here is an example. So in general, we have our SK. This is the encoder kth state, and this is HT. This is a decoder hidden state at time T. We're going to apply a function. Let us call it attention function. Will it produce a score of which applies on HT and SK? So it could be a very simple thing, could be dot product, for example. We get the dot product of HT and SK. So it will be a number, a real number. This is the simplest. You know that the dot product normally measures how close two vectors to each other, or one vector is close to each other, to the other one. So let us say that we have A and B. The dot product is a projection of one vector over the other. So if they are very close, the projection will be very high. Close means that the angle between them is very small. We can have another, this function could be a bilinear transformation like this. So we have H multiplied by a matrix W and then multiplied by SK. So these weights of this matrix will, at the end, we're going to have a scalar too, since we are calculating the score. But in this case, this one is actually similar to this one. The only difference is between the dot product and bilinear. The only difference is what? The dot product is a special case of the bilinear transformation in which W is equal to what?
One
1. W is a matrix. So all ones or what?
identity.
Yeah, W will be the identity matrix. But here, W is not identity matrix. In this case, that it will have different values. This means that we're going to provide uh, uh, more focus on some of the elements of H and S, or it can be like multi-layer perceptron. I mean, another neural network in which we have uh, 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 weight. Here is another vector weight, and here is we have another matrix weight W1, and the hyperbolic 10 is applied on the matrix W1 multiplied by HT and SK. So this, you can look at this as a hidden layer of a multi-layer perceptron, and this is the weights of the output layer, and the result will be a scalar. Okay, so this is the input. The input is H. This is H, and this is S. So this is HT. This is SK, and we have a hidden layer here. So this matrix is W1. So you calculated the H and S as an input, multiplied by W1 to produce the output here. Let us call it L. L will be multiplied by another uh, uh, weight vector, W2, to produce the output.
Doctor, why 10H specifically?
Why what?
Why hyperbolic 10? Why
Because
not
it
any
is,
other function?
yeah, it could be anything else. But it is always good to have hyperbolic 10 will provide output from -1 to 1. So it is always good to have both polars, either positive or negative. If you are going to use sigmoid, it will be always positive, but will constrain the output. The score, it is good that like what we see in here. The score is positive, negative, could be any value. Okay. So hyperbolic 10 is always better than sigmoid, always. But anyways, you can do any function. But at the end, you have to have a score between the hidden state of the encoder and the hidden state of the decoder. So what happens when they did that? So if this is like, this is the input, an input sequence. The agreement on the European Economic Area was signed in August 1992, period and end. And this is a translation in French. So what happens is that the first result of this attention is that the translation is far better. The other thing that actually was not intended, but it came out as a side result, is that there is some sort of alignment between the input and the output. So we have like a matrix here, uh, it goes from white, gray levels from white to black. And here we have the tokens of the input and the tokens of the output. If you look at the value of the attention at every word, like then, first word the, it has black values, very small values with the rest of with all words of the input of the output, except for the first one, which means that there is some sort of relationship between the first word in the input sequence and the first word in the output sequence. If you look at the other word, next word, which is agreement in the input, it only has an effect on the accord. This is attention value. It has nothing. The other values are zeros. And if you look at the entire matrix, you can find some sort of alignment between every word in the input and the other words in the output. Sometimes you can have different values. Like here, the European has some sort of the attention. Of course, it is high with the corresponding French word, but it has some sort of small value with uh, economy in French. Like also the word area in the input has relationship with the uh, these two words. The zone is more associated with areas than this article, and so on. And end is associated with end. So in this neural machine translation, we use the sequence to sequence mechanism in which the encoder is separated from the decoder. The encoder can have n length words, but the decoder can have m length words. Attention is a very powerful mechanism that can weight the focus of or can have some weights or some focus on the input sequence in order to produce the correct output. This has been actually, this attention mechanism was applied in the image caption application that we talked about before. What happens here is that this is the input image, and to produce the caption, they use the attention mechanism, and they found out that if you look at the word, when this word is produced in the output sequence, when they look back at the input image, they found that this part of the image will have the highest attention, which is a frisbee. Same in this image. So we have a dog is standing on a hardwood floor. So when they look at the output word dog, and they look at the attention part in the image, they found that the part of the image that has highest attention value is where the dog is. And then the same for other images, like here we have the stop sign. The attention with the stop part is the highest. And here is the girl, has highest attention, and so on. Different examples. This is a paper, if you want to get the paper. So they use the attention mechanism to produce an image caption. So to summarize this, so it looked first at the LSTM that has a state of the art, and uh, so this encoder decoder used LSTM and use the attention mechanism to improve the translation. And the main objective of the attention mechanism is to provide uh, uh, weights to the encoder hidden state, different weights to the encoder hidden states based on the output required. So the main problem that we're going to deal with next is that the LSTM requires that we iteratively scan each word and wait. This is the main problem. And wait until we are at the end before we can do anything. So we have to enter a word, the start symbol, the first word, second word, until we finish the input sequence, and then we start to produce output. Even the output will be produced one word after the other. But for the input, we have to wait for one word after the other for the input. Although actually we have the entire input available, like the like any statement that we have here, like in the image that we have seen in image captioning, we have the entire image. So why do we have to wait? So we'll do that with the next lecture. Which is the attention. What? Okay. So the first thing that we're going to do here is that we don't have to use recurrent architecture or LSTM. We can do something else, and we'll see how we are going to do that. And sequence to sequence is not only for neural machine translation. You can use it for anything. Uh, we're going to see what is anything is, what is required. And also, neural machine translation don't have to use sequence to sequence, which is the reverse of the statement. But this is the natural thing. So let us see what we let us first go to the first one. That so we need to get rid of using the LSTM or RNN because we need to wait one word after the other. This is a big. If it is, let us say that we need to translate an entire book, so we have to wait for the entire book to be entered. So let us see what we can do for this. So the goal is to transfer or to transform uh, 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 every word in the input into a rich, this is a very important property, abstract representation. This is what we call context embedding. This is different from the word embedding. Word embedding is that we need to uh, 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 represent the word like using a higher dimension uh, vector, let us say of 256 elements, 512 elements. That and the words are the similar words will be transformed to similar locations in the representation space. But context embedding is different. That we the representation of the word will depends on the context, on the surrounding words. Very similar to the skip gram thing or the n-gram thing that we talked about it before, Aid, but here it will be more complex. So by representing every word into this context embedding, this will be based on using weights or weighted sum of other words in the same sequence. So the words surrounding this word will have the effects on how we context embed this word. So we're going to use attention to do that. So the attention will be the tool that will provide the context embedding. So we need to determine how much should this word be influenced by each of its neighbors. And of course, the position of every word is very important. The position is very important if you need to embed the context. So let us go back to the sequence to sequence to see how it worked. This just like a review. Like here we have our this is the encoder. This is our input sequence in French, and the output is in English. This is the reverse. So the last hidden state of the encoder will capture all the information about the sentence, the input sentence. So we have some sort of information bottleneck here. That's the last hidden state of the encoder should represent the entire input sequence. If it is very long, then it will be very difficult for this hidden state to capture everything about the input step. And we're going to use this hidden state to produce the first output from the decoder, and then that's it. This is the only time that we're going to use the hidden state from the decoder. You can actually use it with the last hidden state here. You can use it with every hidden state of the decoder to produce output. So this was not a wise implementation, because we have all words of the input sequence available for the decoder. So why use the last one? This was the question. Why only use the last hidden state, although we can use the previous hidden states in order to influence the output of the decoder? So we have seen that we can use attention to provide some sort of hidden state, and that is a combination of the 4 hidden states here. And this will be added to the hidden state of the decoder to produce every output. So the idea of the attention is that at every state or at every step of the decoder, we use direct connection to the encoder to focus on a particular part of the input sequence. And this is the main issue, that we need to focus on every time we produce an output in the decoder, we need to focus on a different part in the input sequence. And this is, once again, as a representation of how the attention works, but here with the dot product, the very simple thing. So we have our input sequence here. So first this is an encoder recurrent architecture. We first input the first word, we get a hidden state, and then we input the second word, we get a hidden state, third word with a hidden state, fourth word with a hidden state, and then we need to start decoding. So we go to the decoder, we provide the input word, which is a start, and then we provide the hidden state of the encoder. But we need to get the attention, so we get a dot product between the hidden state of the decoder with every hidden state of the encoder. So we get a score. This is dot product. And then, so we get dot product of the hidden state of the decoder with the second hidden state of the encoder. We do that with the third dot product. We do that with the fourth dot product. And then we do the softmax So we get what we call attention distribution, something like this. And it is very clear that on this decoder time step, the first time step, we are focusing on the first encoder hidden state, which represents the word L, which will translate to he. And then we're going to have an attention output, something like this. So we have the 4 words. And then use attention distribution to take weighted sum of the encoder hidden states. So multiply this value by this value by this value by this hidden state, this value by this, add them together and get hidden state. Actually, it should be something like this here. This is this attention output multiplied by this 4 vectors added together, and then we have like a sort of combined hidden state that will produce the first output y1, which is he. So we're going to concatenate the attention output with the decoder hidden state, then use to compute y1 as before. And do the same with when we use hit he we have he here produced here, so we use it to as a second input to the decoder, and then we're going to look back at the encoder. In the conventional sequence to sequence, we never did that. We only looked, the decoder only looked at the encoder once, which is taking just the last hidden state at every time step of the decoder. But here, at every time step of the decoder, it is going to have different context by calculating the attention of the input sequence. So we calculate the hidden state of the decoder for the second time, calculate the scores, which is the dot product in this case between the hidden state of the decoder and every hidden state of the encoder. We get 4 scores. We do softmax. We get these values. We multiply every score. So this is score multiplied by this is score multiplied by this, and this one by the third one, and this one by the fourth one. Add them together, you get another hidden state, another context, and you concatenate this context with the decoder hidden state to produce Y2, and so on. So these are the equations that we talked about, similar to this one, but in this case, we are talking about only dot product. So we have the encoder hidden state H1 to Hn of size H, a vector. On time step T in the decoder, we have the decoder hidden state St, which is also of same size H. And then we calculate the attention score ET, which is, as you can see, it is H1 up to Hn. This is for the encoder. Dot product with St, which is output from the hidden state of the decoder. Dot product between the hidden state of the decoder and every hidden state of the encoder. And this is of size n, in which we have n hidden states. So that n is the length of the input sequence. And then we take the softmax of all ETs, which is alphas. So all of these are scalars. So we softmax them and we get alphas. And then we use these alphas to as the weights of the hidden states. So alpha at time t, sorry, A what the attention output at time t will be every hidden state H multiplied by its corresponding alpha. And this is the context vector that we'll talk about. And then we concatenate the ST of the decoder at time t with the context state that is produced from the encoder to produce a new hidden state of the encoder, which is of double the size to H. This is why I just draw it like this every time, just to show that we are going to have an additional context of the same size that will be used as now the new hidden state of the decoder. So once again, the advantages of using the attention is that it improves the translation performance because it will allow the decoder to focus in certain parts of the input sequence. It will solve the bottleneck problem that before in sequence to sequence, we have everything, every information about the entire sequence just being compressed in the last hidden state. But now with the attention, we solve this problem because at every time step of the decoder, we are looking back at all the hidden states of the encoder. And this will solve the bottleneck problem. And it will also help with the vanishing gradient problem because we have shortcuts to faraway states. Since your attention is based on all the hidden states, so it doesn't matter whether the sequence is short or long, since you have access to all the faraway inputs. And it provides some sort of interpretability. This is the alignment that I talked about before. That is, if you inspect the attention distribution, this matrix, we see that what the decoder is focusing on. Like the word he is, here is actually the reverse. The black is the highest attention. White is the smallest attention. So he is focusing on L, and the white one means that there is no attention whatsoever. So we get alignment for free. It was not intended, but it came out as a side result of this algorithm. And the network just learned alignment by itself. And this is very interesting. So we have seen that attention improves that machine translation, but doesn't have to be attention. I mean, the attention mechanism doesn't have to be used only with a translation. It can be used with any other task, like, for example, classification. We'll talk about that. But in order to use it with any other task, we have to change or we have to redefine how we do the attention. So we have to provide more general definition of the attention mechanism. Like, let us say that we given a set vector values, we have a set of vector values, and we have a vector query. Attention is used to compute a weighted sum of the values depending on the query. You can look at it this way. If you have studied database, the way we read from a database is using a query, right? The query goes to the database and retrieve the records that we need to look at. The records are the values. So attention is as if you are using a certain query to get a certain values or summation of or a weighted sum of certain values, not only one value but different values, and you take some sort of weighting of these values. And they call it the query attends to the value. The query attends to a value. When we use sequence to sequence with attention, each decoder hidden state is a query. And the all encoder hidden states are the values, right? Because we use the hidden state, like the equation here. This is the hidden state of the decoder is our query, the way we ask, and the hidden state of the encoder is the value. And at the end, we take some sort of weighted sum of the hidden states of the encoder using these queries, right? This is, you need to, or they have to adapt to this way of definition in order to use the attention mechanism with other applications, not only machine translation, but with other applications. So one of the things, if we are going to use this definition, then we can have what's called self-attention. So what we need to do is that, I'll go back where is it? Yeah, this one, rich and abstract representation. We need to convert our input sequence into rich and abstract representation, which is called the context embedding. We have done that using sequence to sequence, but we need to do that in other applications. It doesn't have to be translation. And this is what's called self-attention. So we have an input word. As you can see, we don't have any decoder here. We have our input sequence, the brown dog ran. We need to convert these 4 words into another 4 words. So we have x1, x2, x3, x4 as inputs. We need to find z1, z2, z3, z4. As you can see, every word X will be represented by Z, but the objective here is to be much richer and more abstract representation of the input, in which they are going to take into consideration the context or the surrounding words. So we need to have like some sort of transformation here that will convert X into Z. So self-attention is going to do that. So how this is done? So every Z, Z1, Z2, Z3, Z4 will be based on a weighted contribution of the X's. So we have Z1 sort of A1 X1 plus A2 X2 plus X3 A3 X3 plus A4 X4. We need to find these A's, as you can see here, A1, A11, A21. So this one corresponding to the Z. The other one is corresponding to 1 here, 2 is for 2 here, and so on. 3, 4, and 4 here. So the subscript represents the input sequence, the superscript represents the output sequence. So A1I is just a weight. So more is happening under the hood, which means that we need to know how to generate these A's. But at the end, it is just a weighting version of X1, X2, X3, X4. So under the hood, each xi will have smaller, actually, much smaller associated vectors. For example, xi, not one, xi has query qi, ki value vi. So we talked about the query, we talked about the value. We said that the query will attend to the value to produce a new value. The key here is a new thing. But let us say that every input will have three new vectors called the query key and value. So in order to do the self-attention, we're going to do it like this. So let us say that for x1, we're going to have q1 as a query, key1 as a key, v1 as a value. We're going to have these three smaller vectors. If you look at the figure, you'll find that these three new vectors are much smaller than the input embedding itself. So what we're going to do is that we're going to do a dot product between, in order to get the queues, we're going to do a product, matrix vector product between every input xi and a corresponding matrix called WQ, and WK, and WV. What is common here is that what is different is I. So I will differ from, or will go from 1 to 4, as you can see. But the W's, the three W's are fixed. The three W's are fixed. So in this case, we're going to have a sort of, we transform xi into, using matrix Q or WQ to provide the Q1, and using matrix WK to provide the K vector, and matrix WV to provide the V by multiplying with the input vector X. And this will be the weight matrices. Okay, so the first step, we have to have these weight matrices. So let us look at the example here. We need to calculate the scores, which is for the first word, the. Now we are focusing on the first word. We need to represent the word the, which is x1, to produce z1, which is a combination of the other words. So first we have to get we assume that we know now these matrices. We calculated the Q's. So let us say that now we have the Q's. The Q and the K and V are vectors which are already available. So we're going to get the dot product between Q1, K1, Q1 and the K1. So the key vector of the first word will attend to the value of the first word to get the value. So let us just go stepwise. So let's get S1, which is the Q1, the query of the first word with the key of the first word, and we get the value of 112. And then we use the same query since we are talking about the first word. So it is Q1. Q1 is the key. Sorry, is the query that we're going to use with every word, including itself. So we have Q1 with K1, we have Q1 with K2, and we have Q1 with K3, and we have Q1 with K4. So we query This is a query we're going to use. We query we query every word using the query of the first word with the key of all other words. By doing this, you get values something like this. As we know in Python, if in a dictionary, how the dictionary is constructed in Python? Anyone knows?
Key and value.
Key and value. So we have something like this. We have a key and we have a value. And this is going to be repeated in the dictionary. If we need to read any value of any item in the dictionary, how we do that in Python? If we want to get any value,
We call it with the key.
we use the key to get the value, right? We cannot get the value right away. We have to use the key to get the value, right? Same thing here. We have to use the key. The key will give us access to the value. But how can we access the key? Through the query. So you can think of all these vectors as every word will have a value, v1 or v2, v3, v4. And in order to access this value, we have to have a key, like key 1 and key 2, K2 and K3 and key 4. In order to get to the key, we have to query it first. So every word has a query. So the query is used with the key, and the key will be used to get the value. So this is why the first step in order to produce the richer representation is to use the key, the query of every word with the key of every word. So for the first word, you have to use the query of the first word 4 times with the keys of other words. And we get the values. As you can see, this is a vector. Q is a vector, K is a vector. If you get the dot product, you get a scalar value like this. So you get 4 S's, and these S's will be the weight that we're going to use. First, you do a sort of soft max, but it is actually done in a different way. So you divide by the length of the size of the vector key. In our case here, Ki is of size 64. So these vectors of 64 dimension. And you get a sigmoid. So a sigmoid of S4 over 8. Here we have a sigmoid of S1 over 8. So you get 0.87, for example. So these are the weights. The A's now are the weights that we're going to use with the values. So Z1 So instead of using this is directly weighting our original X, which is very long, the dimension is very long. We're going to use with V. When we created, remember, when we created these vectors, 3 vectors, we use the 3 matrices. These matrices will be learned, by the way. We don't fix them. Very much like you can look at these weight matrices, very much like the kernel filters that we used in convolutional neural network. So we're going to use these A's with the V's instead of with the X. A much shorter representation, a more abstract representation. But it is taking into account the neighboring words. So Z1, which is a richer and abstract representation of X1, is equal to A1 V1. So A1 is, as we have seen here, is the query of the first word with its own key. S2 is a query of the first word with the second of the key of the second word, and so on. So we have A1 V1 plus A2 V2 plus A3 V3 plus 0 or A4 V4. Now you can see that Z1 is a combination of the four representation of the four words. And this you get Z1. Same way you get Z2. In Z2, we're focusing more on V2, as you can see here. So it will be A1. So we're going to calculate new A1, new A2. So this A1, A2, A3, A4 are different from those. Those were calculated for Z1. But for Z2, we're going to calculate new A1, A2, A3, A4. We do the same with Z3, we do the same with Z4, so you have four representation. So let us do Z2 again. So we did Z1, right? let us do Z2. We have the same three-weight matrices that we have learned before, WQ, WQ, WK, WV. But now we have Q2, K2, V2. So in this case, we need to calculate Z2. So now we're going to use the query of Q2. Now this is our query, Q2. We're going to use it with K1, with K2, with K3, with K4 to produce S1, S2, S3, and S4. Then we calculate the A's using this equation and sigmoid to get different values. And then we use these values with the V's, with the sum of the V's, so we get something like this. And now this is Z2. We do it again with this Z3 and Z4 to get the four combinations. Now this figure shows what's called the self-attention hedge. This is just to summarize what we did so far. So we have our input, X1, X2, X3, X4, and we get the vectors Q1, K1, V1, and the same with the other inputs. So these vectors are produced using three matrices, W, Q, W, K, and W, V, to produce these vectors. These are much shorter than the original vector, X. And then we use them to produce Z1, Z2, Z3, Z4. This was called self-attention. Why? Because we use the same input to produce another representation that is much richer because it takes into consideration the whole sequence. So Z1 is not only based on X1, no, it is based on X1 and the other three words, and the same applies to every other word in the input sequence. So we have a much richer representation. The context is taken into consideration now, right? So self-attention is very powerful. It produces a context-aware representation. This is very important. It is aware of the context. It is the representation. First, it is smaller, which is abstract. The Z's are shorter than the X. So it is more abstract, but much richer. Much richer because it is taking into consideration the context. So attention, self-attention is similar to attention that we talked about when we talked about sequence to sequence. Very similar. So let us see. Let us answer this question first. What are the key query and the value in the attention setup? that we used in sequence to sequence. So let us look at it this way. So this is the attention that we used before in sequence to sequence. So this is the encoder, and this is a decoder. So what we did is that we calculated the some sort of function between the hidden encoder first time with the four hidden state of the encoder to produce S's, S1, S2, S3, S4, the four score. And then we did some sort of, like here was the softmax. We got A1, A2, A3, A4, right? So in this case, we multiply each encoder's hidden layer by its A1 attention weight. So we multiply this one, A1 by H1, A2 by sorry, A1 by H1, A2 by H2, A3 by H3, A4 by H4 to create a context vector C1D. C1D is, as we have seen before, is A1 multiplied by H1E, A2 by H1, H2E, A3 by H3E, and H4 by H4E. Look at, so this is attention. Let us assume that we are going to imagine that we have applied self-attention to the encoder here, right? So we have S1 is, in our case here, we're talking about, let us say Z2. Q2, K1, S2, Q2, K2, Q2, K3, Q2, K4. We get the A's, and we see that Z, this is actually, it should be Z2, not Z1. Okay, it should be Z1. Q1, 1, 1, 1. Okay, so this is a mistake in the slide. So Q1, 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 K1, Q1, K2, Q1, K3, Q4, Q1, K4. If we need to get the Z1 representation of the first hidden state. Okay, so this is should be the setup if we need to do self-attention with the encoder hidden state. So where are the Q and the V and the K if we're going to apply this? So we have Q K1V for the first hit for this is X1, X2, X3, X4. So for every one of the inputs, we have these three shorter vectors. So where is the mapping? So in attention, we have H1D for the decoder. This will correspond in the self-attention to Q. This is a query, right? Look at here. This is fixed. So this is a query, right? And this will be the keys. If you are going to map to self-attention, this should be the keys, right? And H1 should be, after calculating this one and get the A's, you multiply it by H1, H2, H3, H0. So this will be the values. So by the mapping here, so the query is the hidden state of the decoder. The key is hidden state of the encoder, and the value is the hidden state of the encoder. Now you can convert the regular attention into self-attention if you want to do that. So all of these, the query, key, and value are proxies, abstractions of the sequence to sequence. So they provide flexibility and fewer constraints, but more room for rich abstraction. Okay, so let us take a break, 10 minutes, okay? And then we're going to use this attention to get rid of the LSTM or recurrent architecture and use the transformer. This is the, the, uh, the technique that is used today to do sequence to sequence. Okay, so 10 minutes and we come back or continue after that. Okay.
Please, doctor, we don't hear you.
Yes, doctor, the mic is muted.
Okay, so let's go back. So I kept talking for about 10 minutes and you didn't hear me for 10 minutes. And I was actually going through the slides.
Yes, doctor, we
Oh,
didn't come.
that's
We
really
didn't
amazing.
come for.
So I kept talking for 10 minutes and browsing through the slides and you are not there, right? Wow.
I
That's
thought you
really
were checking the slides, doctor.
and I was writing to myself.
When I saw you writing, I told my colleagues
No,
maybe the
this is
doctor started.
no, no. This is, as you can see, this is the first writing I did, and this was about 10 minutes ago. Anyways, so very quickly, we're talking about the transformer now. The transformer has
so
two parts: encoder and decoder. Very much like the sequence to sequence, we have to have encoder and decoder. So in the for the self attention, we have the inputs x1 up to x4, for example, and then we created a representation called Z1 to Z4, and this representation is much richer and much more abstract, in which the size of Z is smaller, much smaller than X, but it is much richer because it depends on the context. So every word or every Z actually is a combination of the inputs with different weights. And what they did, they added another layer, which is another feed-forward network, to produce another representation, which is R's. So X1 will be R1 and X4 will be R4. It's much more, the main point of adding a feed-forward network here is to make it more even richer and more abstract. But before adding the feed-forward network, since we're going to do training, so in order to avoid the learning problems, so they added two things. The first thing is that the residual connection, the one we used with the CNN before, by allowing the input to add it directly to the output. So in case the gradient is becoming zero, we still have a gradient that is still large. So we can, the updates still can take place. We don't have a vanishing gradient. The other thing is a layered normalization. Before in the course, we talked about batch normalization, in which we have all the inputs in the batch are normalized, which means that it has zero mean and unit variance on the level of the batch. But in layered normalization, the normalization is done on the level of the layer, not on the batch. So this way, the main reason for doing that is also to improve the training process. And the whole thing is the will provide the encoder, but the main thing here is that we are going to have, as we have seen in self-attention, that we have the four or the entire input sequence available immediately. So we don't have to wait to enter one word after the other as we do in LSTM. In LCM, we have to enter the, and then followed by brown, then followed by dog, then followed by ran. So we have to enter every word. But with the self-attention, as you can see here, we use the entire input sequence at the same time. So the Z can be computed in parallel. So we don't have to wait. And this is a huge advantage of using this sort of mechanism to process the input. Now, we don't have to wait. We can process the input sequence in parallel. And this architecture, so we have the self-attention head, followed by residual connection and layer normalization, followed by feed-forward network to produce R. This is what's called the transformer encoder. This is a part that is we use when you enter a prompt on any of the AI tools. It goes to something like this. This is encoder. So it will convert your input, your prompt, into this representation, the R's. But here we have a big problem, huge problem. That is, what's happening now is that you enter your sequence in parallel, like the brown dog gran, and you get representation at the output R1, R2, and R3, R4. This representation actually is a similar, will be similar to if you just change the order of the words. Like if it is like it is brown dog the ran, right? It's the same thing. This one will produce the same representation as the brown dog ran, right? The only thing is that the values of the R's will be just changed. But the context that you are looking for is gone. This makes sense, but this does not make sense as a sentence, right? If you look at the mechanism that we calculated the Z and the R's, it doesn't care about which one is first at all. Which one is first, which one is second, and so on. So the positioning is not important here, which actually does not make sense when we talk about, let us say, translation. The sequence is very important, or the position is very important. So in this case, we have to add something that will take positionality into consideration. Because before that, the encoder looks at the word at the input as a bag of words. Bag, I mean, if you have anything in a bag, it doesn't matter which one is you put first or you put last. At the end, they're all in the bags, right? But for if we need to do translation, we have to make sure that the order is maintained. So we have to add something that's related to positionality, in which we're going to add to the input sequence what's called positional encoding. So we're going to add a vector that will uniquely represent the position of every word. And this actually will be something like sin I, cosine I. I is the position of the word. So it will be another vector. This is an example of this vector. So we're going to have a vector of size 64. A vector. So remember that every word here is a vector. The word embedding, okay? Could be, for example, 256 or 512 or anything. We're going to concatenate with that the position of that word. And the position of that word will be based on this function, sin I, cosine I. I is the position of the word. So if we look at this sin I, cosine I, and the color here represents the value between -1 and 1, right? Since it is sine, cosine, what is the range of the sine? What is the domain of the sine, cosine value? What is the maximum value and the minimum value? Anyone? What is the maximum?
One.
Yes, doctor. Sine, the maximum value is 1. The cosine, the maximum value is 1.
Maximum sign is 1. Minimum is -1 for both.
Okay, that's right. So when you multiply sine and the cosine, the maximum value will be what? +1 times +1, right? So we have +1. I don't know who the other students are talking about. I don't know what they're talking about. It's really amazing. So the maximum value is +1. The minimum value is when this one of them is +1 and the other one is -1. So we have a -1. So this is why we have the range between for this position is from -1 to +1.
They
Now in
were
this case,
discussing about the multiplication of sine and cosine, doctor.
okay, that's fine. Okay, that's fine. I mean, it is not. We cannot discuss while we are talking. Okay, it is just a point of order. Anyways, so the value is between -1 and the +1, and the size of this vector that we're going to have 64. The size of this vector that we're going to concatenate with the embedding of every word will be of size 664. And it is unique, as you can see here. So this is the token position. If it is 0, 1, 2, 3, and so on, this is the embedding dimension, and this is token position from 0 to, let us say, 10. And as you can see, there is no way that every token here has a different representation from any other token. So it provides unique representation of the position of the token. So the embedding dimension is 64. This is when, remember when we divided by 60, by length in the self-attention. So this length is 64. This is why we got an 8 here. So we represent every position as a vector of 64. And these are the different values that we can get. So clearly, it is different. It is for every token position, the embedding is different. And thus, it uniquely represents the position of every word in the input. So the problem that we face here is actually solved by concatenating the embedding of every word with the positional encoding. And this is a very, very important step. So back to the encoder, we have a self-attention head. So a self-attention head, just one set of, every self-attention head will have the matrices WK, WQ, WK, WV. So there is no reason to use only one self-attention head. We can use more than one self-attention head. It's called multi-headed self-attention. Something like this. And instead of having, like here, we have only Z1, Z2, Z3, Z4. Why don't we use other matrices to produce Z1, another representation of Z1, of X1 to be Z1A, Z1B, Z1C. So in this case, we have three self-attention heads. And the same with Z2, Z3, Z4. This is similar to what? We talked about something like that before. This is similar to what? Instead of having one self-attention, we can have many self-attention heads. This is similar to
Yes, doctor, it's similar to ensemble learning.
No.
Similar to having
Is it-
several filters in convolutional neural networks.
Exactly.
Yeah, yes.
Exactly. This is very much similar to having different kernels, different filters in CNN. So we said that we don't have to use only one filter. We can use many filters, right? To extract different representation. The same here, that we're going to use different attention heads or many attention heads for everyone to produce a different representation of the input. This will make the eventual output here very, very rich since you have used different attention heads. Remember that all these matrices are learned, okay? They are not fixed. They will be learned. So we can use multi-headed self-attention. So this will make the representation much, much richer. When you look at the different models in the language models, different number of parameters like 1 billion, 2 billion, 3 billions, actually it relates to this, how you represent your input. Okay. So since when you use 2 billion provides better uh, representation than 1 billion because you have much more attention heads. Okay. So in this case, when we have so many attention heads, doesn't have to be one or two or three. It could be many. It could be 100. It could be 1,000. So in this case, you are going to have very good contextualized embedding R of each word XA. So this is the objective at the end, that every word, every input word will be represented by another word R that is very rich because it's taking into consideration the context, that where it is in the word, in the input sequence. So this is how they represent. Actually, in the paper that describes a transformer, this is how they represent it. That we have an input. This is input. Input embedding will produce the x's. We're going to have the positional encoding. That is proportional to sine cosine. As you can see here, the add here is not an addition, it is a concatenation, I guess. And it goes to self-attention head, multi-headed, as you can see, 3 arrows here. This means that we have multi-attention head and we have uh, uh, residual connection plus normalization before and after the feed-forward network. And so this one is here, followed by the feed-forward network. And after the feed-forward network, we'll have also another layer like this, but it doesn't show in this figure, but we have another layer here, and it goes to the R's. This is one encoder of the uh, or one stage of the transformer encoder. So we can represent the encoder like this as a block. It has input and it has output as a for representation R1 to R4. So why use only one encoder? Can use more than one encoder in cascade. So now X1 will be R1. R1 could be converted into a much richer one called R2. Or L1, L2, L3, L4, and then V1, V2, V3, V4. So the more encoder steps you or encoder blocks you add, the much richer you get. more complex representation of the input you will get. So you have the encoder 1 followed by encoder 2, followed by encoder 3. You get final representation of R's that are actually far, far richer than using only one encoder. So you can stack as many encoder as you want. And this is the same figure, but we have here the word NX, which means that N here is the number of encoder that you are using. So this is why you have different model size for the encoders or for the LLM model. You can have 1 billion, 12 billions. It depends on how many encoders you are using, encoders and decoders. But at this point, actually, you are having what you have achieved is that you converted your input into a far richer representation that is taking context into consideration. This is the main objective now. That's the whole thing. And at the same time, using positional encoding, you have actually maintained the order of the input sequence. So the output is taking into consideration the positional encoding of the input sequence. By doing this, you are actually have converted your input into a far richer representation and smaller, by the way, because R1 is much smaller than the dimension of R1 is much smaller than X1. So you have done some sort of feature engineering. But you didn't do it yourself. Actually, it is done through a deep architecture. So it is not handmade. It is discovered through the architecture. Okay. Now this is the encoder. If you are going to do machine translation, you need what? With the encoder, you are going to need a decoder, right? If we're going to use sequence to sequence, or let us say machine translation, or you're going to convert code written in Python to code written in C, for example, or anything that is you're going to convert something to something else, or a sequence to another sequence. You need a decoder, a transformer decoder. This is a sample of the decoder. So we have masked self-attention head, or we'll say why it is masked. And it's very much the same as, if you look at the entire architecture of the decoder, it is the same as the encoder, almost the same as the encoder. Except for that we have a masked self-attention head. And we have the feed-forward architecture followed by the representation. So the R's will represent the new sequence or the converted sequence. So let us look at the transformer in details. So here we have the input here will be the output shifted right. So we start with the first symbol, and we're going to use now the symbol will be shifted right. So shifted right means that we are going to shift to the right in order to get the new one. So we're going to use S, very much like the decoder in the LSTM. We're going to use the first word to produce the second to produce the third, and so on. And we have to use the positional encoding too, right? We have to make sure that the sequence is preserved. We have masked multi-head attention. This is very much like encoder. We have the feed-forward network here. The only new thing is that we have a multi-head attention coming from somewhere else. So where is this coming from? multi-head attention, what is the normal source of this multi-head attention? There is one, if you look at it, you find that it is coming from, two are coming from something else, and this one multi-head attention is taking it from the multi-head attention, masked multi-head attention of the decoder. So this one is a little bit strange. So where this is coming from, or should be coming from?
From the previous sequence.
No. In the sequence to sequence, the decoder is initialized by what? It's triggered by what? So you
The
enter is
encoder last hidden state.
yeah, by the encoder lost hidden state. The same here. I mean, the decoder in the transformer should be triggered by the encoder, right? So the encoder has to provide something for the decoder to produce. This input is coming from the encoder. So in this case, we're going to have something like this. So let us say that we have 8 encoders in the transformer, and we have 8 decoders in the transformer. And as you can see, the last encoder is feeding back to the 8 decoders. This is where this is. And it is going to produce one word after the other. So let us look at it more in detail, so that the transformer decoders will be identical to the encoders, except they have additional attention head between the self attention and the feed forward network. This one is here. This one, additional one. So the additional one is focusing on part of the encoder representation. It has to use some representation of the encoder to start to produce the output. The key and the value are from the encoders. For this attention head, this one, multi-attention head, you remember that this attention, the self-attention head is using the key and the value to produce the Z, right? And for this one, in the decoder, it uses the key and the value from the encoder. Remember when we did the comparison between the attention sequence and self-attention? We compare the value and where the value and the key are coming from. Same thing here. So we're going to use the key and the value from the encoder to produce the representation for this multi-attention head in the decoder. So now the decoder takes something from the encoder. It has to use something from the encoder in order to produce output. The query, key, and the value for the transformer self-attention head, not the attention head, the self, the one, the lower part, this one. Are all from the output of the previous decoder layer. Either from the decoder layer or from the produced output. The transformer decoder also has a positional embedding, just like the encoder, right? So this had, in order to produce the output in the correct position, it has to provide some sort of positional encoding as well. But this is where the masking is playing its role here, that every position, each position is only allowed to attend to the previous indices. That's it. So this position only attend to this one, and this one attend to these two. So when they produce the output, they have, if it is still producing this one, they have to mask this. If it is producing this one, it has to mask, if it is producing this one, it has to mask every other or the coming words. And this was called masking here. So we have to mask the words that's still to be produced. So each position is only allowed to attend to the previous indices. So this is just another representation of the encoder decoder. If you go to this blog, it actually has a very nice explanation of the encoder decoder. So this is the encoder. We have uh, uh, the encoder only two layers. The decoder is also 2 layers, as you can see here. So we have, here is input with positional encoding. So we have self-attention, normalization, and residual input, and then going to feed-forward network with normalization and residual input. So this is the first encoder, going to the second encoder, and so on. In the decoder, we have masked self-attention, normalization, and then we have the encoder-decoder attention. This is the above attention head, followed by normalization, followed by feed-forward network, and then normalization. We have the second decoder, which is exactly like this, and then we have a linear layer, followed by softmax. So softmax here is for what? What should be output here?
It's a probability from 0 to 1.
Of what? So what is the size of the softmax here? How many neurons here?
I think the number of vocabulary.
Number of the words in our vocabulary. That's right. So if you look at this figure, you can see that we have from decoder, last decoder, as you can see here, we have, it goes to decoder 2, it goes to decoder 1, goes where? Goes to the encoder-decoder attention. Okay? Goes to encoder-decoder attention. What is the input to the decoder? It is only the positional encoding. It is only the positional encoding. And the output will be the translation, let us say, that of this input here will become output here. Okay? As you can see, it's very simple architecture, but when you add too many layers, it will become very complex. So let us look at just, this is an animation of what's really happening. So this is the first time step. Okay. So here we have an input sequence in French. We need to translate it to English. We have 2 layers of the encoder, we have two layers of the decoder, okay? And the representation here is, this is a representation. So it goes to the representation, and then we are going to go to the decoder to reproduce the first output, which is I. Let us look at it again. So first we have the input, then we have the embedding, then embedding with time, which is or position, goes to the encoder, produce an output, the R's. First time, second encoder goes to the representation, and key and value go to the decoder, first layer, second layer, and then the output will produce an I. Let us go to the second step. So let us just go back. First step, we did that. We'll produce an I. Go back to the second step. We have an I here, right? It produced an M. And we used, note that in the decoder, it has to wait. Now, it does not produce the output in parallel. For the encoder, we present the input in parallel. But for the output, for the decoder, it actually use every input to as every output as a new input.
So basically, the encoder translates word by word, and the decoders decides the order, right?
No, the encoder does not translate word by word. The encoder represent the entire input sequence with one vector, like this.
Okay.
Okay?
Yes.
But the decoder will produce the output word by word, as you can see here. And actually, this is what you see when you use any LLM. You get the outputs word by word. Maybe you don't see it word by word because it's very fast. But if you happen to use one of the local LLM, if you know how to use something like Olama, for example, you will find that it is because it is using your machine, which is very slow. You will find that the output is produced word by word.
Thank you.
Okay. So this is the architecture of the entire architecture of the transformer connected together. Here you have N encoder layers. Here you have N decoder layers. As you can see, the only difference between the encoder and decoder is that you have that the first multi-head attention is masked in the decoder because it has to prevent the autoregression, or it has to prevent words from that will come later to contribute to the current step. And you have a multi-head attention here, which is taking its input from the representation of the self-attention head of the decoder and from the encoder, from all the layers of the encoders. So this means that from all the ends. So this is N connections, NX connections. And it receives key and the values from the encoder. But the rest is the same. The last one is just to produce the correct word. There is a positional encoding in both the encoder and the decoder. So when we train this transformer, we have to find a loss function. So the loss function is a cross entropy that we talked about before, predicting translated word. Training times, it was for this application, it was 4 days on 8 GPUs. Sometimes actually it takes months now, depends on the application. But for this particular slide, it was a certain application that it took 4 days on 8 GPUs. And this is the complexity per layer for self-attention, recurrent, convolutional, and self-attention. Are you aware of this notation, the O notation and the omega notation? Have you heard about the O notation or the complexity notation?
Used to calculate the time and the space it takes.
The time, omega for the time. Okay. O for
The
the
big
time.
O.
Yeah, the big
Yeah.
O for the time and omega for the space. So when we say that it is for self-attention, it is order of, this is why it's called O, order of n squared and times d. So n and d is the dimension of the input and the number of input dimension and the output dimension. Sequential operation is also order of 1. If it is this is complexity per layer, this is sequential operation. If you are doing one operation, so it is 1. But for recurrent is n because it is done n times based on the input sequence. Anyway, so I'm going to leave this for you to go through. So n is the sequence length, d is the length of representation, the embedding. Is the complexity of self-attention good or not? This is self-attention. Is it good or not? If you look at these values. So try to think about that, about this question. So one of the things that when to answer this is that when learning dependencies between words, you don't want to have long paths, right? You don't want to have the first word or the last word dependent on the first word if it is very long. In this case, the maximum path length will be very, very, very big. So you don't want to have this. Since in self-attention, actually we have everything is parallel, so it is the maximum path is 1, right? We don't need to wait. So in self-attention connects all position with a constant number of sequentially executed operations. So, but in RNN, you have to wait for n samples.
So the first one in the table is better than the restricted?
So this is n squared d, this is r nd. So this r is less than n. So it is better. So the last one is better, of course.
Okay.
But the maximum path length is, here is 1, but here is more than 1 because n is greater than r.
Okay.
So this is the blue loss for different architectures, different sequence to sequence. Like here, we have English to German and English to French. And the training cost in flops, English to German, English to French. These are different architectures. Like we have convolutional sequence to sequence. Here we have reinforcement learning ensemble. These are all ensembles. And here we have the transformer, base model, and big model. So if you look at the loss for blue, this is for transformer, it is actually blue has beaten everyone by 41.8. And this is in French, but in German, it is 28, so it is better than everybody else. Training cost, it is also better than everybody else. The cost in flops, it is smaller than everybody else. And this is why the transformer was a big hit. This is what you should do when you do research, that you should, if you say that your model is worth publishing, is that you have come up with results that are fit better than the state of the art. At the time when the transformers came out, these were the state of the art. So you have to say that I'm better than the best one so far in order to get published. So state of the art at the time of doing this representation. So what using transformer that you can train to translate from language A to language B. And you can train to translate from language B to language C. Without training, you can convert from language A to language C. And this was huge. So you can have code written in C transferred to Python, for example. You can train on that. You can train also on Python to Java. Then you can, if you have a code in C, you can convert it to Java right away with the same architecture. Now we have seen the transformer has encoder and decoder. So what it does, it actually decode and translate. This is what it does. What if we don't want to do that, but we need to use the capabilities of the rich representation? Let us say that our task is classification. Can we do that or not? So what if we need to focus more on the rich representation, that we need to have far better representation of the input, given that the input has some sort of context, right? So we can also provide much richer representation. We can have the positionality to be more explicit. We can use it for, let us say, CNN instead of only using it with transformer. Can we use it for in CNN or not? Same concept. What prevents the positional encoding from being used with other architectures? So these are all questions that actually arise from using the transformer. One of these things is that, like here, these two actually are addressed by BERT. BERT is actually, when it came out, it was very, very famous and very heavily researched. And there are many variations of BERT came after that. BERT is for bidirectional encoder representation from transformers. Bidirectional in the two directions. Encoder representation. So we're going to use encoder of the transformer for richer representation. So like bidirectional LCM, but it goes in both directions. So you can have the representation is both directions. It's only using the encoder part. There is no decoder in this BERT algorithm. It provides a richer representation. So the objectives of BERT, the first one is to predict the masked word. Let us say this is our input. The first one is the start of the symbol. Then the second word is masked. The third word is dark. So it has to predict the second word, the masked word. And it came back with three values like brown, lazy, playful, with brown having the highest probability. So in this application, 15% of all input words are randomly masked. 80% become mask, 10% become revert back, and 10% become uh, deliberately corrupted as wrong words. So these are the way they try to train this model. As you can see, it has eight encoders. The second objective was two sentences are fed in at a time to predict if the second sentence of the input truly follows the first one or not. So it is if one sentence is actually a natural follow-up after the first one. So it was very, I mean, it has to make sense. So this objective is to make sure that the paragraph being written is making sense. Why? How? So where is this coming from? This is coming from the richer representation that it has acquired through the training. So I'm not going to go through everything here, but I'm going to just started it for you just to go through that. This is a paper of the BERT. Try to download and read. It is very interesting. So I just included the slides for you to have an idea of what BERT is doing. There are many, as I said, many variations of BERT, like Roberta, like Berta. So BERT is for very much rich, contextualized embedding of words. And it can be used for transfer learning for classification. Actually, you can use it for very much like when we use CNN to classify input of an image, you can use it to classify a certain text here. But it does not generate new sentences. It is because it does not have a decoder. Okay? It just provides very rich representation of the input. That's it. Okay, so we still have about 10 minutes or so. So let us go to the autoencoders. Where is it? Yeah. Autoencoders, what's that? Everything we have been discussing so far is supervised learning. Everything was supervised learning, that we know the input and we know the output. Okay? Now we are going to do something else. We're going to do unsupervised learning. That we have no labels, we have just data. That's it. With the Dr. Jibiji, you are doing the third type of learning, which is reinforcement learning, which is actually a combination between the two. So the supervised learning and the unsupervised learning. Because in reinforcement learning, we don't know the target, but we have like a cue to the target. We know that, I mean, if you are playing chess, this is a game. We use reinforcement learning to play any game, including chess. We can decide whether the move is correct or not, right? So this is the when you get a reward or you're gonna get a punishment in reinforcement learning. You partially have an access to the target, but you don't have the target itself. So the target is somehow hidden. The entire target is hidden, but you have a clue to where, if you are going to the right position or not. Here in the autoencoding, we are going to do totally unsupervised learning. Just to give you an idea why this was important, if you look at uh, something called autoencoding, this paper, autoencoding variational base. This paper came in 2013. In 20, actually, in 2020, I guess, this was a number of citations for this paper. This for this guy. This guy, young good fellow, who's the one who wrote the famous deep learning book. Goodfellow produced his GAM paper. We talked about it later, 2014. In 2020, it has citation about 27,000 times. This shows how important this deep learning for unsupervised learning has become. So what we're going to discuss here is the latent variable models. Latent just means hidden, okay? And then principal component analysis and autoencoders. We very quickly we will be talking about variational autoencoders, but we're not going to waste much time. But we are going to start with the latent variable models. Latent means hidden, is not visible. So before getting into that, let us just review what supervised learning and unsupervised learning are. In supervised learning, we have a data set pair. We have the input xi and the output yi for I from 1 to n. So these are all known. So the input and the target. Classification, regression, any prediction is sort of supervised learning. For unsupervised learning, we don't have the y's. We have only the x. We have just the data, xi. The examples for that is clustering. You did that with, I think, with Dr. Marwa, clustering, dimensionality reduction, generative models. This is what we are going to talk about. Some of them use latent variables to capture structure. And this is what we are going to do here. We need to capture structure by discovering the latent variable. So what is that? LVM or latent variable models. So we need for LVM, we map between observation space That is, X is D-dimensional space to latent space Z, which is Q-dimensional space. And normally Q is far, far less than D. So we have a variable X, or we have a sample X. We we need to find HZ in lower dimension space. Z represent the what's called the latent space. And from Z, we can have another function G that can provide us back with a version of X hat. Okay. So we are going to have two, this is why it's called autoencoder. So we have F is the encoder, G is the decoder. F encode the input X to Z, and the decoder decode Z back to X. And this is what's called, it is called autoencoder. Z is the latent space. Why? Because it is converts the input, which is very large dimension, into the smaller dimension. So every input X will have its own Z. So, and Z is in dimension smaller than X, so it is doing some sort of compression. So these models, F or G, could be linear or nonlinear, could be deterministic or stochastic, could have a encoder or not. So in this table shows some examples. If it is linear and deterministic, then this is the principal component analysis. I think Dr. Marwa talked about that, right? PCAs, right? Or not?
Right, doctor.
So PCA is linear and deterministic. If it is linear but stochastic, or it has some sort of probabilistic nature, it's called probabilistic PCA. If it is nonlinear with encoder, it is called autoencoder. If we have an encoder, it's called the autoencoder. If it is stochastic, it is called the variational autoencoder. So variational autoencoder has an encoder and a decoder, but it is stochastic. If it is nonlinear without encoder, this is very difficult. There is nothing deterministic here. There is no model that can do that. But we have models, stochastic models, that can do this without encoding, which is the generative adversarial network. We can do that. So very quickly before we go, I'll just do these two slides, and then next time we will start with this one. So autoencoding, we have our input X that goes into an encoder with the function fw to produce Z. Z dimension is, this is dimension D, this is dimension Q, and we use a decoder, a function G. It has, of course, we have some sort of weights here to produce X hat of dimension D. The objective is to have X hat very close to X. So we're going to find W's by minimizing X hat minus X, the L2 norm of X hat and X. So this way we are going to produce the encoder and the decoder. And these models are called autoencoders because they autoencode the X into X hat. We're only interested in Z here. This Z is the most important part that we are looking for. They are called autoencoders because they predict their input as output. So one would say that this is actually some sort of supervised learning. No, it is unsupervised because we use the input as output. So the target is input, and in this case, it is called it is classified as unsupervised learning. In the generative adversarial network, this is the next topic. We're going to use only the decoder. This does not exist. We're going to start from here. So in the GANs, we are going to, our input will be Z to produce X hat. Very interesting application, but we're going to see how it's going to work. So we're going to have our encoder. For example, here, let us say that this is the MNIST digits that we all know now. The MNIST digit, we have an input image, which was 28 by 28 pixels. As you can see, a 7, I guess, 764, something like that, dimension. Here we have a compressed representation. This is Z. So this is X, this is Z. As you can see, 1, 2, 3, 4, 5. We have 2 by 5. We have only 10 pixels representing the 76.4 pixels. And we need to use these pixels, these 10 pixels for the decoder to have a representation of this digit with the smallest error. And this is why we use autoencoding in compression, data compression. We use it actually in image compression, and we use it to produce more data. And as we are going to see next. Remember when you do data augmentation for CNN, for the CNN, we can also use it, data augmentation, by using the autoencoding mechanism. So I'll stop here. And on Wednesday, inshallah, we will start talking on details on how to do that.
Doctor, please, can I ask some questions?
Yeah.
Regarding the project presentation video, I personally plan to use my own voice for the presentation or for the video.
Not only you, the entire group has to present.
So it's not allowed to use AI generated text to speech voice, right?
That's a really interesting question. So you need AI to represent you?
No, I'm asking.
You are actually outsourcing the work that you should do yourself to AI. So you are actually telling me that I'm going to cheat. Is it allowed or not? The answer
Not
is no.
allowed.
You are not allowed to cheat. Okay.
Okay.
Actually, we have spotted. Speaking of that, in quiz 1, we have spotted many written answers that have been written by the AI. I'm going to allow it this time. I'm going to overlook actually this time. Next quiz, if that happens, you will get a 0 and you will fail the course. Okay?
Doctor, please.
Is that
Dr.
clear or
Hazem.
not? For everyone, it happened.
Doctor,
Just let me finish, please. It happened in the first quiz. Many students use AI. So this is cheating. In Queen's regulation, this is cheating. Actually, this will result in actually you fail the course and you will be kicked out of the program. If I actually pursue the official procedure, you will fail the course and you will be kicked out of the program. So we spotted many situations. Was very clear, like someone actually was using LaTeX code in the answer. You don't have the time to write LaTeX code, and the answer was very long. When we say that it is a written answer, it should be very short. You don't have the time to write that long answer unless you are using AI. Okay. If it happens again in quiz 2, I swear I'm going to apply Queen's procedure and you will fail the course. And you know the consequences if you fail the course. You will be kicked out of the program. You will the entire cost of the program will be incurred in you. You have to pay back.
We actually agree with you, Doctor.
Don't
We
take it
agree.
lightly, okay? It is not an Egyptian university. They are very strict. When it comes to cheating, they are very strict. And the system actually easily detected that you are actually using AI. They have, this is why we use it in online. We have a tool that tells us that this code or this answer is flagged with AI very easily. I can't. Well, I have the names. So this is a very strong warning. I'm not going to warn again for quiz 2. If it happens in quiz 2, you will fail. Definitely you will fail. Okay? I'm not going to say that again. Okay, other questions?
Doctor, I have a question.
Yeah.
You said someone used the latex and that's like AI, but there is actually embedded latex option in the written exam.
What do you mean?
There is an option to write a small latex equation in the written exam.
That's right. I
prompt.
know. I know
Yes.
you can do that. Did you have the time to do that?
Yes.
Okay, good.
No, doctor, I think we need more time for the next
No, you
quiz.
don't need more time actually. You need more time because you need to write a lot. You are not supposed to write a lot. The answers are very short. This is another problem. The answers are very short. You have only 5 written questions in 90 minutes. Right? 90 minutes. You have 5 written questions. That's it. The rest are multiple choice and true and false. So the time is actually huge. If you are going to write the most compact and straightforward answer. But if you want to write a long answer and you want the grader to pick the right answer from your writing, this is another story. We don't do that. If your answer is long, you will be punished for that. When we say it is an online exam, then it has different characteristics from the written exam. It has to be tight in time. First, not to allow you to, unfortunately, you can go and use AI uh, and do all sorts of things that students normally do. But when it comes to written answers, it should be short. It's called short answers. Actually, in the definition of the question, it's called short answers. So I'm not going to change anything. Okay, I'm not going to change the weights of the quiz. I'm not going to change the time. The quiz 2, it will be similar to quiz 1. You have to study very hard. This is Queen's is one of the best 4 universities in Canada. So it has its own standard. We're not going to change the marking based on the level of the students. If the students level is not up to the university standard, then it is very bad. Okay, you have to work very hard.
Can I ask about something, Doctor?
Yeah.